Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So the subject, generally speaking, is energy. I'll give you some of the history and all the evidence, I would argue, that's pretty decisive in pointing out that physics has made a mistake in defending this modern, and it is modern in the sense that for hundreds of years, people who thought about the physics of the mechanical function of the universe sort of got the idea that mass and velocity was a controlling factor, and even to the point where Descartes basically said there's only so much of this mass and velocity in the universe, and it's just migrated from one object to another object to another object, and this is this quantity conserved. And then the competing theory rose in around the 1750s or 60s with Huygens and then Leibniz, making the argument that somehow this thing, this living force, as Leibniz called it, was the quantity that was actually conserved in the universe, and that the real shape of energy is this formula 1/2 mv squared. For Leibniz, it was just mv squared, because they were using the same units to foot-pounds. Anyway, what now is called a Newton. So anyway, and like this has been a problem in physics from the very beginning, is this fact that they have all these different ways of measuring energy in terms of the heat or horsepower or calories or thermal unit. I mean, it's just there's not one understanding of this is a unit of energy. It's in all kinds of different manifestations. So I would certainly argue that energy is just mass moving, and that the thing we call force that moves stuff, that has mass, and it does cause things to, it exchanges its mv in the sense that it shares its mv with other objects, and the mv has to be conserved. If you add mass, you have less velocity. If you reduce the amount of mass, you have more velocity. It's that simple. And that's all there is, and that's all there ever was. And it does make a conservative sense. And you could argue that the law of the lever that came way before any of that conversation basically tells you that the MVs have to match, that the thing being conserved is just the mass and the velocity. A 2 mass going 1v is the same as a 1 mass going 2v, that kind of simple logic. All right, so Leibniz took the argument basically from Huygens, and there was no argument provided with it. It was just a statement that said that this mv squared is a real thing. And Leibniz used the example that a 4 mass dropped 1 foot would be the same as a 1 mass dropped 4 foot. And he just said that it would be the same. There's no evidence that he had any experimental proof that it is the same. Now, Galileo had done all these experiments and kind of isolated the function, and so there isn't really much room for a discussion about what actually happens with gravity. Now, Newton made it even more quantifiable in the sense that Newton established that it's 9.8 meters. Well, he was using feet, so I'm not going to bother with that. Units of velocity increase. Okay, so it's 9.8 meters per second. Okay, of an increase in your velocity in 1 second. So every 1 second you gain 9.8 meters of velocity if you're free falling. And if something interrupts your free fall, then obviously what you're going to gain is you have to add up what you lost. So if there's any applied friction, then those numbers aren't going to be true. But if there's no applied friction to take any of the energy away, you can have the expectation that every 9.8, every 1 second, you're going to get 9.8 meters of distance. velocity. In distance, it's only going to be 4.9 because it takes time for the 9.8 meters increase in your velocity, okay, to happen. It doesn't happen instantaneously. It takes time. So when you put something on a scale, it takes time for it to compress the spring. It doesn't do it instantaneous. It doesn't have 10 pounds of weight, instantaneous weight. It has weight applied over a distance and an amount of time. So anyway, the simple truth is, okay, if we use these as 1 second units of distance, so let's just say this is how far it's going to fall in 1 second. So that would be 4.9 meters. So it's 4.9 meters of distance, okay, and it's going to take 1 second. All right. Now we know that this is going to do the same thing. This one mass is also going to do this 4.9 thing in 1 second. So this is 1 second of time. So these two experiments are going to look very much alike. And the simple argument is if I was to do that experiment, this weighs 4 times as much as that. I have every expectation that this is going to hit the ground with 4 times the energy because it has 4 times the mass. So we know that experiment, okay, is pretty decisive that this one has the greater amount of momentum by a long shot. So now we're just going to give this 1 more second, and in that 1 second, what's the expectation? Well, it's going 9.8 meters per second, so it traveled 4.9, but it's going 9.8 meters per second. So even if I don't add any more force, so I don't add any more gravity, we know it's going to get this much, okay, in the next second. It's going to get these 2 units of distance. It's going to get 9.8 meters of distance because it's now going 9.8 meters per second. So it's going that speed, it's going to travel that far, and I don't have to apply any more force. But the point is I am going to allow it to travel for another second. I'm going to do another 4.9, okay, I'm going to add another 9.8, and the simple truth is it's going to hit the ground going 19.6. So everything works out. It's going twice the velocity. So it's twice the time, okay, and it's going to be twice the velocity. All right. And they say, because it's going twice the velocity, I have to square the velocity, so it's 4 times the amount of energy. And so they're basically saying that the one mass in the gravity for only 2 units, only gaining 2 units of gravity, somehow is going to equal the 4 mass having 1 unit of gravitational pushing. And again, it just doesn't make any sense. Okay, it's not going to add up. It's not going to conserve momentum, clearly, and there's no reason to think that it's somehow collected, that this somehow is 4 units of energy when it's only 2 units of time in the actual force. So if you thought of the force as being something that was raining or pushing, like paint spray or something, and we're just saying how much paint spray was collected, it could only collect 2 units of paint spray. It could only collect 2 units of whatever this stuff gravity is. It only collected 2 units of it. And yet they're saying that those 2 units are somehow 4 units. Even though when, like I said, when they do the experiment fair, they know that this is 4 times this if I drop them the same distance. And they're somehow just saying that twice the time in the force somehow is 4 times the energy. So they're saying that anytime you double something's velocity, you quadratically increase. So you have 4 times the energy. So if you run into something twice as fast, you somehow hit the wall with 4 times the energy. And there's no evidence that that's true. So they haven't done any experiments to demonstrate this, and they haven't done this simple experiment. So nowhere in physics is this experiment written up as a paper, and where it's demonstrated that if you drop a 1 mass 4 distances, 4 units of distance, that somehow it's going to equal a 4 mass dropped 1 unit of distance. And it's just a statement. So physics is basically endorsing the statement, because they're endorsing the conclusion that somehow this theory is correct, and that somehow it's absolutely true that if you go twice as fast, you have 4 times the energy. You go 3 times as fast, you have 9 times the energy. Now, the reverse is also true, which means that if you're going to move something, you need 4 times the energy to move it twice as fast. So that's their argument. You can't throw something twice as fast unless you apply 4 times the energy. You couldn't throw it 3 times as fast unless you applied 9 times the energy. And so this all goes all the way back to something like driving a car. And so their argument is, whether you know it or not, okay, it takes 25 times the fuel to go 5 times as fast. That somehow the machine must consume 25 times more energy if it's going to go 5 times as fast. And that's the only way they can make their theory conservational. And obviously nobody has that personal experience. So they're basically saying that if I have an electric drill and I spin it at, 5 rotations, 10 rotations in 10 seconds or something, that to go 50, 5 rotations, 5 times faster in that same time, I would have to apply 25 times the electricity. So, and anybody who's done any mechanical work knows electric motors don't work that way. You want to go twice as fast, you apply twice the wattage. You want to go 3 times as fast, you go apply 3 times the wattage, not 9 times the wattage. So all this started with just the statement that this existed, and there was 70 years of controversy until Madame Chartelet imposed herself into the argument. And France actually had a contest, basically saying somebody prove which theory is correct. Somebody demonstrate it, and we'll give you a prize. And the fact is they didn't demonstrate it. Nobody did it. Nobody made an argument with anything called evidence. They just again reasserted axioms that weren't true, and so it really wasn't advanced any. Now, what Chartelet did was provide an experiment, okay, done by somebody else, and it can be understood to be falsely premised in terms of not logically defendable as a way of measuring real energy versus something that you might call apparent energy. So I will deal with those type of arguments first. I guess why we have this drawing just should keep in mind. So again, this is 1 unit of time for this, and then the second unit of time is all of this. And that's just because you have changed the velocity, obviously. So it's the same amount of time to do this as it was to do that. All right. And it just should be understood in terms of observing that the object is going 1/2 its velocity here. Okay, way up here. 1/4 of the distance, it's going half the velocity. And so that will be relevant to other experiments where you're going to see exactly the same outcome. And again, it looks like something, but what should be recognized is that yes, you're not going half your velocity at half the distance, and that's a big giveaway that you're not losing or acquiring energy at the same rate. That every unit of distance here you're going much faster, so you're gaining less from the force because you're going through the force faster. Alright, this rolling example provides pretty much the same argument. So if you imagined this just turned vertically to horizontal, you could see that this would be the same as dropping something, and you could say that it's all basically got Galileo's ratios in it. In the first unit of time you would travel 1 unit of distance, and the second unit of time would be 3, and then the third unit of time would be 5 and then 7. It's the odd numbers. And so it looks, if you look at it, you say, okay, so if I roll two equal objects, same mass, and I roll one at twice the velocity, and then we have them going those velocities at this exact moment, and then we allow friction to consume the energy, to take away their velocity. The truth is the friction is going to take it away the same way it was acquired. That is, it isn't acquired in, instantaneous chunks of velocity. It takes time to acquire it, and you only go half the distance of the velocity you acquire. So you'll decelerate at the same uneven rate at which you accelerate. So in this simple experiment, twice the velocity will get you 4 times the distance. But the key point again is that you'll be going 1/2 your velocity here. And this experiment will be the same as this experiment. In the sense you'll be going 1v here, okay, and you only travel this short amount of distance. And the simple truth is that as you're going faster here, starting at 2 velocity, the higher velocity means the friction has less time to work on you. You're going across the surface faster, and by going across the surface faster, it's not until you start slowing down that each unit of time you're having more force push you into the friction. So you're losing more and more energy the slower you go. So the slower you move across the scale, the more you'll weigh. So if I did take a very heavy object, I moved it very quickly, you can imagine the scale wouldn't even notice at all because I moved it quickly enough across the scale. Kind of like flying buses in movies, right? It's kind of fake, but the idea is if you're going fast enough, you can't fall down because there's not enough time to fall down. So you're defeating gravity by moving very quickly. And the idea here is you don't have to move that quickly to understand that you're going across each unit of distance faster. The faster you go across that piece of surface, the less the surface can absorb your mass, your weight, because it hasn't had enough time to absorb your weight because you're going too quickly across the surface. So you can also illustrate that as a gravitational body in space. And the idea is the faster you go, if you go very, very fast, you don't get bent at all by it, okay? And the slower you move, the more and more time gravity has to push you into the surface. So time matters. It's a time-dependent force. So the idea is that in this whole section of 1 unit of time, okay, and this is 1 unit of time, same time to do this as it took to do all of this, that it's the same amount of gravity over this much larger distance. So per unit of distance you're getting less force. The total amount of force will be the same, and that's why you lose half your velocity in this long distance, and then you lose the other half in this smaller distance because the times will be the same. So it's only twice the time. So even though it's 4 times the distance, again, just like in gravity, it's only twice the time. And the ground is only going to absorb twice the energy, because that's all you have is twice the energy. So if they could do experiments where they actually measured the heat put into the ground, it's obviously the friction is absorbing all of the energy. Both objects are going to stop, and they're going to stop because all of their energy was transferred from being in their linear motion to being in the heat in the ground. So if you did actually measure the heat, you'd recognize that it's only twice as hot, this whole surface. And this whole surface is you're spreading it over 3 times the area, so you could understand that it's going to be 1/3 the heat because you've put it into at least 3 times the mass. So it works fine. It fits with what Galileo observed. Obviously, if you're going faster, you're covering distance, you're covering more distance in the same amount of time. And it's really just about how you absorb the energy. So if I did do the experiment in space, obviously the 2 velocity is only going to travel twice as far. in the same amount of time, because nothing's taking the energy away. So it's the fact is this in this experiment's a good experiment proving the point, in the sense that you're basically saying, well, what's the possible energy that this can possess based on the fact that it is in fact moving across the surface faster, making less contact with the surface, therefore the surface is absorbing less of its energy. So you could sort of think of it as electrical contact. And the more electrical contact you're making, the more amperage you can put into the conductors, and you transfer. And the less contact, the less you can transfer. So if you were to drop objects and use wind, okay, to push them into a surface. So if you had a surface and you drop things right next to the surface and use some force to push them into the surface, the same rules would apply. The pressure you're applying this way is essentially defeated by the distance you're traveling across the surface. So the faster you travel upside down, you're getting the same amount of push this way over a much larger distance. So your pounds of pressure you're putting per square inch changes. So it's all just about time. It just matters how much time the force is bleeding you, rather than how much distance you're traveling. So the distance isn't going to tell you the truth about how much energy you had. The heat in the ground will tell you the truth. All right, so related to that, all right, another classic type experiment done where they'll argue that it's demonstrating something to do with kinetic energy being conserved, and it's, just a say-so kind of argument, is you have a 5 mass going 10 velocity, okay, and then what you do is just add 5 mass to it. And it really doesn't matter whether you add the 5 mass gracefully or not, okay. What you're going to end up with, okay, is a 10 mass, all right, going 5 velocity. And you're going to perfectly conserve the momentum. Now, they're going to argue that this has twice the kinetic energy that this will have in the end. So you're going to lose 1/2 the kinetic energy. So 50% of the kinetic energy is going to be missing. Yet you have nearly 100% of the momentum has been conserved. So, you can have this just a millimeter above this when it goes by and they combine. And you're going to understand the combining force is really gravity, so they're not going to have a problem where you have a competing velocity. So you're going to preserve your velocity this way. And it's just a simple demonstration that momentum works, that it's perfectly conserved. And their argument that something happened here, when you combine these things, that somehow you created sparks or friction, or you broke pieces off, or you made something hot. Now, there's absolutely no evidence of any of that. And if there was that stuff, then you'd have to believe that you can make heat, or you can make pieces fly off and not use any momentum. So that's a rather preposterous proposition, that somehow I could actually make vibrations in the ground, and I could do all kinds of sound, and I can do all kinds of other stuff, and I don't use any momentum to do it. So I conserve every bit of the momentum, and yet there's other stuff moving in the universe somewhere. So that's free momentum again. Not a possibility, not a possible explanation. So again, it's just another experiment where they claim it. They say, look at it, and so in this case, obviously you look at it and you say, yeah, well, it looks like conservation of momentum, right? And you lost 1/2 the kinetic energy. That's a lot of energy to lose. So if you thought of this as a 5-ton train, it's an awful lot of energy to lose. A 5-ton train going 5 miles an hour is what you've lost, half the energy. That's a lot of energy. So it doesn't make any sense. It doesn't fit. And clearly you can't conserve momentum and then claim something else actually happened, that there's energy somewhere else in the universe. If you have all of the momentum, you have all that the thing had to give, and there isn't anything other to give. And that would be the simple argument. So this relates also to a ballistic pendulum, which I'll get to later. But we'll we'll go back to the historical narrative now. So I'm just saying these are experiments that existed. They aren't really referenced in any of the debate, and that's the part that's a little bit strange, is that they're pretty decisive evidence, if analyzed, that there's no room for kinetic energy. It doesn't make any sense, and it doesn't show itself to be capable of ever doing anything called real work. Alright, so back to the historical record. So in about the 1730s somewhere, a Dutchman, I think, did these experiments where he dropped metal balls onto a clay surface. And a woman called Madame de Chartelet in France found out about those experiments and demonstrated them to the scientists of Europe, and as an argument defending the theory that twice the velocity is 4 times the energy, because when you took 2 equal objects and you dropped them into clay and you only dented the surface of the clay, that is, you didn't penetrate the clay, the fact is you could get a ratio of displacement, that is how much area was created in the crater, of 1 to 4. So even though it's only twice the velocity, it was displacing the clay 4 times as much. There was 4 times as much clay removed. Now, these are physicists of the 1720s, and so who knows how much physics they actually knew and how much of their physics is religion and a bunch of other crap. So the guy who invented the experiment, who did the experiment, was a believer in perpetual motion, and he traveled the world. Anytime somebody said, I have a perpetual motion machine, he'd go out and check it out, because he did believe it was possible. And you could see why he would believe it's possible, because the kinetic energy theory, frankly, does create free momentum. And free momentum sounds like good stuff if you can get it. That would be a way to make a perpetual motion machine, is to make a machine that makes free momentum. So anyway, but I argue that the physics isn't that hard to figure out, in terms of this is just basically a pointy arrow kind of argument. That the more pointed your arrow, the further it penetrates into a surface. So that's not even a debatable subject, right? I mean, everybody should be able to concede that, yes, the more pointy it is, the less flat the tip is. So if I made 2 arrows, one with a flat tip, okay, and one with a pointy tip, I can be quite assured one of them's going further with the same energy into whatever it hits. And the same is going to be true for a round surface. So you could understand, as a round surface penetrates, it changes its shape depending on how deep it goes. So at each level of depth, the shape of the object making contact with the clay changes. So you can see at the bottom, it's very flat. So a very flat surface is hitting. And then as you go a little deeper, you're now getting to a better surface. It's not quite as flat. And then it gets even more sloped and even more sloped. So now you're pushing clay sideways and not pushing clay down. All right. And so the overall percentage of your angle, so if you were to take this little flat bit and then add it to this bit and then add it to this bit, and then you'd end up with a final average of a slope. And so the deeper you go, the higher that slope. So essentially just saying the pointier your arrow. So you go from an arrow shape like this to an arrow shape like this. Okay. And that's the simple reason why this penetrates less, is because the arrow that was making contact with the clay, the average surface angle was, this, and the average surface angle here was something like that. And so that's why you got more penetration and displaced more clay, is because you were pushing it sideways instead of pushing it down and then sideways. So you were doing less work on the clay, is the simple argument. And no doubt the clay was getting less hot. It got hotter here and less hot here. Another simple way of understanding it. So I'd argue that, if the science was up to the task of being able to properly analyze all the geometry and recognize this stuff, they would have gotten right answers. Now, I'd say that somebody like Galileo, if he was asked the question, I think he would have been able to figure that out, that the surface is changing the deeper you go into the clay. So if they had done the same experiment and allowed the clay to penetrate and then figured out how far it fell into the clay, you would have the same averages. Once you go past the midway point, then it's all the same for both surfaces. Both are using the same point on their arrow. So once you go past halfway, it's the same all the way the rest of the distance. So there wouldn't be any more substantial difference between the two in terms of the slope of what they're encountering the surface with. The slope would be the same, and you'd end up with the same displacement of clay. So some of these experiments have been done in an amateur sense, and that was what was found, that if you penetrated the clay, it didn't come out to be 4 times the displacement, and if you just dent the surface, it does. But again, this fooled people. So it looks like a real experiment, right? It looks like it's real. You're dropping 2 objects. One of the objects is displacing 4 times as much clay. It looks like it would say, oh yeah, it takes 4 times the energy to do that. But if you think about pointing arrows, you can realize that you can go a lot deeper into something with exactly the same energy by just changing how you contact the surface. So how the 2 surfaces interact with each other, the condition of them as they interact changes the interaction. Simple enough. So that's the 1720s. That was a kind of a decisive moment in terms of convincing people, and but again, there wasn't any hard analysis until we get to Joule and Lord Kelvin. Alright, so we jump 100 years from de Châtelet 1730 plus to Joule 1850 or so. We have another effort to quantify what energy is, how it works. So Joule was came from a family full of people who were very interested in science, but they were basically running a brewery. They made beer. And he was in the point where the steam engine was being developed, and he had a question, and the steam engine plus the new thing of electricity, the electric motor. And his real inquiry was some way to test which one was more efficient. So which one could you get more work out of? And he needed a way to quantify. And so he ran into the problem that exists, and that it's hard to design a perfect experiment. Like the rolling ball, for example, it's hard to measure the heat into the ground. There's always a catch in terms of doing an experiment and trying to convert energy from one form to another form that you can measure every single bit of it. So he came up with the idea of a Joule tank. And the idea is to have an insulated tank full of water, and now you're going to move the water, and the water is going to have a proportional increase in temperature. So we first established that happens, that as you agitate water, there's a proportional increase in its temperature. And now he could have things pull on a paddle, spin inside a tank of water, and measure how much heat they could produce. So he's basically turning all of their energy into something he could measure in a tank, the heat. So this is like rolling the ball, except now he has a tank that measures exactly how much friction is being absorbed out of the object. So how much you're taking from something. Now the problem with the experiment is this part, okay, where he didn't tie it to a horse or tie it to a moving car or a carriage or something like that. He dropped things in gravity. And the problem with dropping things in gravity when you're applying a frictional force against their falling speed is that they don't fall at the same rate. They fall at completely different rates based on their mass. Heavy things fall faster because they apply their energy quickly, because they have more force, they collect more force. Lighter things collect less force, therefore they fall much slower. They turn things slower. So they're in the gravity a longer amount of time. So if you only have a set distance for something to fall and you drop a heavy thing, it's going to be out of the gravity very quickly. That is, it's going to apply a lot of energy to the paddle very quickly. It's going to fall very fast. The light object has to move the heavy paddle. It's not going to move it quickly at all. So it's going to be dangling in the gravity a much longer time. So it could be in 10 times as much time to fall as the heavy mass would take to fall. And the argument is that the whole time that mass is being affected by gravity. So the longer you're resisting the gravity, the more work you're doing. So at the same time as this, and maybe 50 years later, conversations about the fact that their physics is basically saying if I'm holding a mass up in my hand and I'm not moving, I'm not doing any work. And you know that if you were holding 10 pounds, you're going to have to do a lot of work to hold it in that position. You're going to have to do all that work against gravity. Each second, gravity is going to be applying force, and you're going to have to counter it each second. So the amount of time you're holding it is going to have make a huge difference in how much work you're going to have to do. So weightlifters defeat that by trying to get the weight moving as fast as possible. The faster they can get it to a height, the less work they have to actually do. And the slower they lift it, you can imagine if a weightlifter deliberately lifted the weight slower, he's going to be doing a lot more work. Now, people who weight train know this, and they know not to jerk weights because that doesn't do them as much good. And so they always lift weights slowly because you get more out of it. You have to do more work to lift the weight. Okay, and it's the same thing for lowering a weight. You can tell you're doing a lot of work. The slower you lower it, the more work you do. So that was a huge flaw in his analysis, was the fact that he wasn't accounting for the fact that the time that it's in the gravity is going to decide how much energy you're actually resisting, how much force you're overcoming. So the slower you make the weight fall, okay, the slower the object moves and the slower the weight falls. So that means a heavy object, say if I was just dragging, say if I didn't bother with Joules' tank and I just dragged a weight. If I dragged a very light weight, it's going to fall, this weight's going to fall very fast and I'm going to get very little energy out of it. But if I take a heavy weight and drag it, then this weight will drop very slowly and I'll be in the gravity much longer, getting hit by the force of gravity. And so I'll get a lot more energy into the thing I'm moving. So the heavier the object, the more energy I'll put into it. The lighter the object, the less energy. So this sort of relates to a spring argument that's also peripherally related to this subject, in the idea that when you launch something with a spring, you won't get the same energy into the object no matter what weight it is. So if I launch something light, when it leaves the spring's still moving very fast. So if the light thing's going to go 30 miles per hour, the spring's still moving 29 miles per hour when the thing leaves. And if I launch something very heavy that's only going 5 miles an hour when it leaves the spring, then the spring's only going 5 miles an hour and I have a lot less energy stored still in the spring. So I'm going to be a lot more efficient in getting the energy out of the spring the slower the spring has to move. So it's exactly the inverse of the weight argument. But it's obviously understandable that, yes, if the spring's doing this after the experiment, that means all of that energy it didn't get into the object. And if the spring's just doing this, well, that means that I got a lot more of the energy into the object. So these are, again, this is physics. the physicists should be able to figure this stuff out. And I guess the simple argument is they didn't think about it much. They just went with whatever everybody else was agreeing was the truth, and they didn't bother recognizing that, well, it violates some fundamental laws, like the law of the lever, for example, which we'll get to. And, it's really solid physics, the fact that MV is real stuff. It's not, momentum isn't some nothing. It's a very real something, and it does have to be conserved. You can't make free momentum, and all of these experiments imply that you can somehow derive more energy out of the same energy, and you can't. More motion. So that takes us to Joule and Lord Kelvin, and again, so it's not that the experiment isn't valid. It's not that the Joule tank doesn't work. It's just that, you have to understand that this height you're not dropping it in free fall. It's not falling at the same speed. And things not falling at the same speed shouldn't be assumed to have the same energy. If I drop something and it falls at the same speed, well, I can say it's the same energy. If they're dropping at different speeds, you'd have to understand something's got to change. Something's got to be different about the two things. All right. All right, so since the mid-1800s, there is no experiment to highlight. It's just little rickety experiments where they bang carts into each other, or some sort of air track stuff, or something else, pendulum, something. But very little qualitative anything. And so questions like this have come up, and physicists have actually written books basically telling bowlers that they're better off using a lighter ball at a higher velocity, because they'll get more kinetic energy out of the ball, and somehow it will put that energy into the pins. So by their theory, an 8-pound ball going twice the velocity, 16 velocity versus say 8, would deliver twice as much energy. And that what would equal the same amount of energy would be a 4-pound ball, so 1/4 of the mass thrown at twice the velocity would somehow be the same energy. So obviously you can understand, if that's going to be the same energy, I definitely can throw something that's 4 times lighter twice as fast. You could even argue I'm more likely to be able to throw it more than twice as fast, and therefore able to get more pin action out of the ball. And so clearly things like this don't happen in reality. There's zero evidence that bowlers can make any of this real. They can't go to 10 pounds and take advantage of the little bit of extra energy. They can't make any of it ever work, is the simple truth. No professional bowler uses a lighter ball, because it just doesn't happen. Their prediction isn't true. It's the simple truth. They're better off not paying any attention to physics in this case, because it won't help them any. There's a chance, if the odds are, the facts are, you can only transfer the momentum of the ball anyway, because we have no way to ever collect this extra kinetic energy. So they can say it exists, but they can never collect it. So you can't collect it with a ballistic pendulum, you can't collect it with a rocket engine, or with a rocket even encountering some particle in space. It can't collect the kinetic energy, it's only going to collect the momentum. Car collisions are always analyzed based on momentum, not kinetic energy, because it's only the momentum that's going to decide where something moves and how it moves. So even though they have all this evidence, this compound evidence demonstrating that momentum will decide outcomes, they just keep claiming that this is real, this kinetic energy thing, and that these outcomes would really happen if they were tested, but they never test them, so they don't get proven to be wrong. And it's a simple truth. So again, their statement is, their physics directly says, that to move something 5 times faster, that is to spin something 5 times faster, you have to apply 25 times the energy. That's what their physics says. And there's just no example where you could ever have that happen in reality, where it takes 25 times the energy to spin something 5 times as fast. It's just nonsense. And I shouldn't have to make these videos. It's the simple truth. So we'll go through all the other ways, all the things it violates. And so here's the modern error. And I guess the next thing I'll talk about is the Steve Mold. He's a person who gets millions of views on YouTube as a science presenter. He makes the claim that levers don't conserve momentum. And nobody challenges it. Not a single other person besides me. Yeah, that's it. No one says, what do you mean? You can't not conserve momentum. I can play Professor Lewin. I can play all kinds of professors saying, you've always got to conserve momentum. You can't lose momentum. And clearly, you can show the very same principle in an oscillator where there's no place for the energy to disappear to. You can't destroy the energy and then recreate the energy, then destroy the energy, then recreate it. It has to be in the system constantly going back and forth. That's how oscillators work. They trap energy in the oscillator. And the oscillator can't change how much energy it has. It's a silly notion to say it can. But anyway, so there's just tons and tons and tons of evidence demonstrating that 1/2 mv squared is just a fable. It's just a story somebody told 300 years ago, and they're still telling the story as if the story has some credibility, and it's Goldilocks. It's Little Red Riding Hood. It's baseless, made-up mush, and it's terrible physics. It's terrible science, and honest people should just acknowledge that, yes, it's unevidenced rubbish as an idea. All right, so here we have 2,000-year-old physics that, nobody complained about. And nobody even complains about it now, except when they have to defend their new conventions that are in direct contradiction to these old theories. So it was an old reliable theory that you could just say the distance times the mass always had to be conserved on a balance, a lever, a stick, anything with a fulcrum. And the distance is completely proportional to the velocity. So obviously if I move this 1 inch here, it's going to be 2 inches here, okay, twice the distance. So you're guaranteeing that you're also increasing velocities of objects in an oscillator configured this way. Now, kind of sorry about my lack of clear voice. Anyway, so I did this with a 4-to-1 ratio on a balance, that is something suspended from above, so it was a balance. I guess I might as well go through the difference between these levers. And obviously a 1 mass going 4V equals a 4 mass going 1V. And completely contradicting any notion that a 1 mass going 2V somehow equals a 4 mass going 1V, which it doesn't, because it's not the same momentum. So levers conserve momentum is the simple argument that was observed. And the MV on this side has to equal the MV on this side for it to balance. Simple truth. So you can have a small mass and a big V over here. You can have a big mass and a little v over here, and those things will equal each other and balance. So it's by showing you what weights equal each other, and what weights equal each other is essentially the same thing as saying what momentums equal each other. And that's what it proves. And it's been demonstrated thousands or millions of times now, and that's what they're saying doesn't happen. So they're saying that if I was to put a 2 mass in with a certain amount of energy into this side, I won't get a 1 mass at twice the velocity out on this side. I'll only get a 1 mass at 1.4. And that I could put a 1 mass with only 1.4 velocity in this side, and I could actually make a 2 mass go 1 velocity and create free momentum. So it's that easy to make free momentum. I just take a light thing going fast, push it into one side of a lever, and I can make more momentum in heavy things going slow. Almost infinitely, like the bullet example, for example. I could put I could theoretically. And the example of a bullet is another good example of why kinetic energy fails, because it's not an equal and opposite reaction of the gun. The gun recoil is 2 joules of kinetic energy. The bullet has 2,000 joules of kinetic energy. So where's the equal and opposite reaction from the explosion? Obviously there isn't one by their theory. Alright, so here's one example of an oscillator. So this will oscillate. If you suspend something from above, a lever, what you're basically guaranteeing is that as the lever changes its positions, it switches where the mass of the lever itself is, guaranteeing that it will keep oscillating in gravity. So on a surface that has gravitational force, you can put masses on it and create an oscillator, and it will continue to oscillate until slowly but surely it loses all its energy to a little bit of heat in whatever the suspending wire is and whatever you're using as a fulcrum. And so it can be hundreds of times of oscillating back and forth. And what will oscillate are these masses. The lever is balanced, so there's an equal amount of mass on both sides, so we know there's nothing in the lever itself, okay, that could account for any differences. And so you basically just have added 4 mass here, okay, moving 1v, and you have a 1 mass over here moving 4v, and it's perfectly oscillating. That is, it's pushing up into gravity and then being pushed down by gravity, and it just keeps doing that over and over on both sides. Now, what theory would there be to be arguing that this has 4 times the energy over here? And that's what their claim is. How can that possibly make any sense? That there's 4 times the energy on this side of the lever oscillating perfectly? So the 1 mass going 4v is 4 times the energy, but this side over here oscillating only has 1 unit of energy? There has to be the same amount of energy on both sides of the oscillator. So it's just, you can't it's pretty decisive. I don't see how there's any way to deconstruct that into anything that could make any sense for kinetic energy to be real. Now, the simple truth is the oscillator isn't that complicated to figure out why it happens. So what happens is when this lever goes from this position, the neutral position, to some other position, what's going to happen is essentially this center line is going to change. So you're changing this dimension, which means you're changing this center line. This is the fulcrum, the top. So the whole lever swings over, which means there's more mass on this side. So it just basically is saying you've taken this much of the lever over here and you've put it essentially on that side of the lever. So as it rises, there's more and more stick going out that way, meaning there's more and more mass on that side of the lever. And so it slowly gets heavier and heavier and heavier. That's why it slows down and stops. And now it falls because it is heavier. And when it gets to the neutral position, then it's back to being balanced. But it's going to overshoot, of course. And the other side's going to be lifted up with the energy you initialize the system with, the oscillator with. And that extra energy is going to keep oscillating back and forth between the two sides. So you can't possibly come up with some rationale that says, there's 4 joules of energy over here and there's 1 joule of energy over on this side, or vice versa, 4 and 1. There's no rational way to say that happens. Alright, so the other levers are, if you configure the lever with the fulcrum in the center, then you can understand that, well, you're not shifting the mass. The mass is staying exactly even on both sides, so there's no change in the mass. So I could take the 4-to-1 relationship again, and I could swing it into a position and it'll stay there. I could swing it into a lot of different positions and it'll just stay, because there is no compensating extra mass being created. So it won't oscillate, it'll just stay in a position once the friction consumes the energy, or it'll just keep rotating. So if you put energy into it, it might just keep rotating, because this won't get heavier, it won't slow down. So it'll just keep rotating. And the third option is to have a fulcrum below. Okay, and that one's the decisive one, where it's all or nothing. So if you get the balance just perfect, All right. Then it's okay. It'll balance. But any imperfection is going to do exactly the opposite of this lever, where the mass was being put on the side, okay, that's moving. It's going to be the opposite, and in terms of which side gets the mass. So the side that's getting heavier, that is the side, the side moving down, is now getting more mass thrown on it. So the side gravity's decided, or you've put energy in and pushed it down, it's getting more mass put on it, so it's going further down. So it's all or nothing, essentially. So a fulcrum at the base means if it's close, it'll be okay, it'll balance. But anything to cause this side to go down or this side to go down, and it'll stay down. So I could have perfectly equal masses. I could put one end up and one end down, and it'll stay that way until I create enough energy to compensate for the extra mass I've put on the side that's down. And so it can be used as a balance, but it's the kind of balance where you have to keep resetting it, because it won't balance by itself. You have to balance it. You have to establish it as an equality and then see if it fails, and then fix the failure until you get it right, because it's either balanced or fails completely. All right, so I guess that's enough on levers. Now, what Steve Mould said about levers not conserving momentum, this 1.4 thing, they also say the same thing is true for pulleys. And obviously it's not. Okay, pulleys also conserve momentum perfectly, fine. Tiny losses to rope friction. So, you can set up a pulley where you move a mass 1 unit of distance out here, and it moves 2 units of distance here, or 3 units of distance, or 4 units of distance. But the momentums are what's always going to be conserved, and the kinetic energy is not. And those are absolute facts, and if they tested it, it would be an absolute fact. If they tested this lever, they're not going to get this 1.4 result. Okay, it's not going to happen. Because it doesn't happen, because it doesn't make any sense to destroy the momentum. Where could the momentum possibly go? All I did was put pressure on this side of the lever. If I press on this side of the lever with my finger, and then I put the 1 mass 2 units of distance, it's going to weigh a certain amount. If I put the 2 mass half that distance, it's going to weigh exactly the same amount. I'm not going to be able to tell the difference between those two weights. It's the same requirement to provide energy to move the object. The objects require the same energy to be moved. A half mass requires to go twice as fast. It's the same energy as a full mass with 1 unit of velocity. Fact. Proven by other experiments, car crashes and such. Alright, because it is a fairly related subject, catapults, and then you get to cannons and guns and all kinds of arrows even, lots of mechanisms for launching objects. And the simple rules known for thousands of years, okay, is that you could pretty much guarantee that, especially in the case of a trebuchet where you're using a weight, okay, and it's going to swing and push an object, the trebuchet is going to move the same speed for both objects. So if I have something that weighs twice as much at half the distance, the force it has to apply is exactly the same as the force it has to apply to move the half mass twice the velocity. And those rules always did work and still do, and there's no room for kinetic energy. There's no notion that it has twice the kinetic energy, that it can do twice anything, that it can do twice the work, or that it takes twice the work to produce it as an object. It doesn't take twice the work. It takes exactly the same amount of work. The same stored spring tension in a catapult is going to be able to do those two things. Launch the half mass at twice the velocity, the full mass at 1 velocity. Alright, so and then these are things Newton knew about. So he knew what a cannon was. Okay, and the idea that it shoots the cannonball and there's an equal and opposite reaction. Now, I would argue it's the wrong way to say it, because there is no equal and opposite reaction. There's just a transfer of energy in a direction. So if I have $10 and I give somebody $5, there was no opposite reaction that made me $5 poorer. I'm $5 poorer because I gave away something. So obviously, when you're giving away this way, you're going to have more of that way left over. So if you have a balance and you give away half your balance, you don't have the balance anymore. So is the simpler, I think, argument. And clearly explosions are, by their very nature, equal. In the sense they're going to push both directions equally. And so you could say that something like a cannon or a gun, the explosive is moving at a very high speed, thousands of miles, maybe hundreds of thousands of particles of miles an hour, versus the speed of the cannonball. So it's really not going to matter whether it's 10 pounds heavier or 50 pounds heavier. It's the speed of the force is so much faster that you're not going to have any differential. It's not like wind pushing on a sail, where it would make a difference if you're going 30 miles an hour and the wind's only blowing at 40. Obviously, it gets harder and harder to push something, but it's not going to get harder and harder in these cases. But anyway, so the simple argument is Isaac Newton recognized that no, the cannonball doesn't have more energy than the cannon itself. There's an equal and opposite proportion of the energy. The cannonball has half the energy of the explosion. The cannon has the other half in principle. Same is true for the gun and the bullet. So the kinetic energy theory says the gun has 2 joules of energy, kinetic energy, and it says the bullet has 2,000. I mean, an insane differential. Clearly not an equal and opposite reaction in any sense. Now, the fact is, if I calculate the momentums are going to be exactly the same. So that physics, again, works perfectly, and it's perfectly consistent with the idea that I can't change what the explosion produces. So taking this to a further extreme, it could be understood that... All right, so if I had a steel pipe and I put different mass bullets in it, so just the bullets are going to move, the pipe isn't, zip gun, so to speak. By their theory, I can change how much power the explosive has, how much measurable power, by just putting heavier and heavier bullets in. The heavier the bullet I put in, by their theory, I'm going to somehow change how much momentum I'm going to get out, and I'm not. I'm going to get the same momentum out, no matter how heavy or light I put the bullets, because the explosion is moving so fast that it's not going to really care whether it's 10 ounces or 10 pounds. And the fact is, I will conserve the momentum. So the lighter the bullet, the higher the velocity I'm going to get, and it's always going to conserve momentum, and it's never going to conserve kinetic energy. So I put heavy bullets in, I get a very low kinetic energy. I put light bullets in, I'm going to get a very high kinetic energy. And so I'll be able to say that somehow the explosive creates more kinetic energy depending on what it's exploding. And again, that's just another form of a free energy formula, saying that somehow there's a maximum amount of kinetic energy it has, and the maximum amount would be the heaviest bullets, and or the lightest bullets, and then the least power it has is to put the lightest bullets in, and it's just wrong. So all of this is all in their physics, in the sense that they say a single cosmic ray could knock down the Empire State Building, because it has so much kinetic energy, because it's a little tiny mass moving almost the speed of light, and therefore it has this incredible amount of energy. But it really doesn't. It just has momentum, and its momentum is 1,000,000 times less than its kinetic energy. And it's momentum that really does work. Kinetic energy doesn't do work. It won't do work on these bullets. It won't do work on a cannonball. It doesn't ever do any work. All right, so moving on. All right, moving on to classic spaceship kind of argument. So whether it's lifting off, or whether you're navigating in space, or turning it, or however you're doing it, the idea is you're going to produce something called thrust. That is, you're going to take some kind of matter and you're going to push it at velocity, and you're going to hope to get the equal and opposite reaction. And you won't get the equal and opposite reaction to anything called the kinetic energy. So if you understood it as little pellets you were shooting out, The idea is if you calculate the kinetic energy of your little pellets, all right, the KE, you're going to get a number, okay, and it's going to be a multiple of times, depending on the velocity, greater than the momentum. So if the momentum is 2, your kinetic energy is going to be 200. That kind of disproportion will always exist, and the faster you make them particles go, the higher that disproportion or that difference in the momentum and the kinetic energy gets. But the only thing that's going to move this spaceship in this direction is the momentum. So no matter what you do here, the momentum's the only thing that's going to make anything happen here. So let's say you did shoot these things at 10 miles an hour, right? You need a certain amount of energy to do that, to propel them. So now if I take 25 times the energy and move these little things 5 times velocity, so I plus 5 now, so it's 5 times the velocity. You're saying I have 25 times the kinetic energy here, but I don't. I only have 5 times. This is only going to go 5 times faster. It's not going to go 25 times faster. So even though I use 25 times the fuel, I'm only going 5 times faster. But anyway, the point is that the KE, okay, doesn't get put into the ship. The ship doesn't get the KE. It only gets the MV of the thrust. So whatever you throw out of here, even if it was Volkswagens, it doesn't matter what you throw out of here, some mass moving a velocity, that's all you're going to get into the spaceship. So they keep saying kinetic energy is the definition of energy that does work. It clearly can't do work in the most elemental environment you can get, empty space. In empty space, it can't do any work. The fact is, if I have a tennis ball in my hand in empty space and I throw it and I give it a certain kinetic energy, the only thing it's going to give me, the opposite reaction, is its momentum. I'll never collect the kinetic energy. It doesn't matter whether it hits me, it doesn't matter whether I throw it, doesn't matter how it happens, no matter how the interaction happens, I will never collect anything called kinetic energy. It'll never be transferred to me, to this object you want to move. So obviously, there would be no advantage in using all this extra energy to make small things go fast. And if you were in space, the real advantage would be is to make big things go slow, because you use a lot less fuel. But the point is, it's not going to matter, because the fuel really is just momentum making. Momentum runs the universe. And these simple experiments, these simple even thought experiments, you don't even have to physically do it to understand it being true, prove the case. It's an absolute proof that kinetic energy doesn't do work. It won't be transferred from one object to another object. It will not be conserved in the universe. There's only momentum conserved in the universe. That's the thing you can never destroy. That's the thing you always have to account for where it is. So again, you can't take a 5 mass going 10, make it into a 10 mass going 5, and then claim you conserved all the momentum and lost half the kinetic energy as heat and deformation and pieces flying off. You can't do both those things because you can't use momentum twice. All right. Next. Alright, so an experiment closely related to the 5 mass going 10 versus 10 mass going 5, and the gun and bullet and the rocket. This ballistic pendulum experiment, classic scientific experiment, always comes out decidedly saying kinetic energy is crazy, and yet they keep doing it, keep proving the case in a sense. That it's a complete failure as a theory. It doesn't make any sense because it never is able to do work on the pendulum. Okay, so you make a heavy pendulum full of some gel or clay, and then you shoot a high-speed projectile into it, and your whole point of doing the experiment is to see if you can collect this thing's energy. And the fact is, you can if you understand energy as momentum, because you will conserve the substance of the momentum. Now, the slower you make the object go, the higher the percentage of the momentum, because yes, you'll create less heat in the substance doing the catching. But even with bullets, where you have something like 2,000 joules of energy going in, the fact is all you're going to get is 2 joules of energy coming out. You're just going to get the momentum. That's all you're going to get in the pendulum. The pendulum's motion will not collect the kinetic energy. So if I use a ball bearing into a mass that's only a few times heavier, the fact is I'll only lose half the kinetic energy or some lower number percentage-wise, and the faster the object goes, the more. So with a bullet, it's 99.94% of the kinetic energy doesn't go into moving the pendulum. And the point they say is it made a bunch of heat. Thousands of joules of heat. 1,900 joules of heat. Okay, more than that. And the argument is well, how can you conserve this much of the momentum? That is 95+% of the momentum is completely conserved, and the momentum's only 2 joules, and yet you produce 1,900 joules of radiant heat, which is the same thing as momentum, motion in the universe. You've created a bunch of masses moving, little tiny masses moving, and you only use 5% or 2% of the momentum to do it. So you created thousands of percent more momentum in the environment, but you collected almost all the momentum you started with. So again, it's a huge, we just created a bunch of free momentum. So when they tell you this energy is in there somewhere, they're just telling you. There's no evidence. They never stick a thermometer, okay, in and prove there's 1,900 joules of heat in there. They never demonstrate it, because the only heat that's in there is this little 5%. It's a tiny amount of heat relative to the motion of the bullet, percentage of its energy. The fact is the ballistic pendulum did collect most of the momentum, and that's the same thing as collecting most of the energy. And so in every single case, there's never been a case ever where a ballistic pendulum collected 101% of the momentum. Just 1% more, which would have meant 99.97 instead of 0.4% of the kinetic energy lost. So even a little bit less of the kinetic energy lost would have mean more momentum collected. But it never happens. Ever. So it loses 99% of the kinetic energy. It conserves 99% of the momentum. And yet the claim is that there's some magical losses here of 99% of the energy is someplace else besides motion of the mass you can see. That there's some sort of invisible motion that's taking place, and you didn't need anything's momentum to make that invisible motion. You didn't need to use any momentum to do it. It's just so illogical. So again, decisive evidence this has nothing to do with work, especially. So to have the definition of the kinetic energy formula to be, this kinetic energy does work, when in every example it doesn't do any work. It gets dissipated as heat every single time. So when I put I have the 5 mass going 10, and I add the 5 mass, somehow I lost half the kinetic energy dissipated as heat. It didn't do work. And I end up with something that has exactly the same momentum. So I've lost the kinetic energy, and I have the same momentum. How does that make sense as a proof for kinetic energy? I mean, it's obviously a proof for exactly the opposite, that it's always been a fable. It was always just made up mush. It never had any real credibility experimentally, and I shouldn't have to make these videos. Fair, reasonable, intelligent people who have any knowledge of these subjects at all should concede that, yes, it's perfectly clear the evidence demonstrates kinetic energy doesn't do work. It doesn't move rockets. It doesn't shoot boulders. It doesn't do any work, ever. Momentum does work. Momentum knocks over bowling pins, not kinetic energy. Alright, so I guess we'll sum up with this experiment. There are others, fluid dynamics, hydraulics, that all demonstrate the same truth, that momentum does work. Kinetic energy is a waste of your calculation time. It won't do you any good to calculate it because it won't be transferred in an experiment. So anyway, this test has been done. Now, the Mythbusters did it with cars. They actually did crash a car at 50 miles an hour, then crash the same car at 100 miles an hour, and it was only crushed twice as much. So twice the velocity, twice the crushing of the car. And then they even did it to the extreme of crushing them this way, and obviously both cars got 1/2 the amount of crushing. So, and no demonstration that anything but momentum is deciding how much energy is being applied in collisions. So in this test, this is a Bruce Yearney with wooden blocks, and it's a pretty good example. With a rubber band between them, stretched the same 1 meter, and then they crash into each other. And so you take a 1 against a 1, obviously the crash happens right in between the distance-wise. And they both go pretty much do the same thing. They just bounce off of each other, bounce in the air a little bit, do some stuff, but the collision itself doesn't move from the point of impact. It just stays there. Then you do it with twice the mass and the rubber band, and you know in principle what happens. Everybody agrees that the heavy thing will have 1/2 the velocity. The collision will actually happen, demonstrating 1/2 the velocity in the sense that it'll be 2/3 of the 3/4 of the distance. The fact is, when the two things collide, this one is stated to have twice the kinetic energy, and this will be 3 times, and this will be 4 times. And in each case, the collision happens because this is moving slower. Obviously, the collision happens at a different location, but in each case, the collision doesn't move in the direction of the thing with 4 times the kinetic energy. So the kinetic energy, again, fails to do work. It fails to do work on these objects. Not one of these objects that are, well, these 3, where the kinetic energy for them is much lower than the kinetic energy of the object hitting them. In any one of those cases, does that extra kinetic energy do any work on those objects? It doesn't push them that way. And the fact is that in all car crash analysis, they use momentum, because momentum will decide. If I give one of these objects more momentum, in this case, all of these things have exactly the same momentum. The MVs equal the MVs for all of them. And it's the kinetic energies that say there's different energy somewhere. And the demonstration of the experiment is that no, there's no demonstration of any extra energy anywhere, any unevenness in the energy. Momentum rules. So if I actually did do the experiment and I made one of these objects have more momentum, I can't do that with a rubber band, but I pushed one with more momentum than the other one. It wouldn't matter whether it's lighter or heavier. The only thing that would matter is it has more momentum, and the thing with more momentum is going to win the collision. The thing with more momentum, if I could reverse this and allow these two objects to swing past each other and have a tug of war, the fact is the tug of wars are always going to come out this way. Kinetic energy will demonstrate itself to be useless, and all that's going to matter, the thing that's going to win the tug of war, is whoever has the most momentum. That's a fact. These are facts. I'm just saying that's decisive evidence saying kinetic energy doesn't play any role in the physical universe. It doesn't have any reality. It's, again, just something made up 350 years ago, like a Holy Ghost, and you're still believing in it because they say so. Not because they've shown you so, but because they say so. And even to the worst extreme, where one of the top science presenters on YouTube makes a video claiming that levers don't conserve momentum. Even to that extreme, where they say something contradicting thousands of years of physics, the law of the lever, and they don't do it. There's no accountability whatsoever. Not one person will stand up and say, I don't believe in Holy Ghosts. I mean, show me. I didn't know physics was a religion. You have to believe in the dogma. I have to recite a catechism. It's really bad. All right, so we'll call that a video. It could use improvement. Bad voice day, all that. So I'll probably do it again in the future. But anyway, it's just for the sake of the website, essentially. And documenting the fact that physics has made some catastrophic errors. Not thinking gravity is a force, catastrophic error. All right, not understanding that energy is momentum, and that's all you need to know. If you want to see energy in the universe, you just find a mass moving, and that's energy in the universe. Completely quantizable energy in the universe. All right, anyway. And then the wave particle stuff is just entanglement. You fall for that crap? Come on. There are better answers than their silly religion.